For some reason, I've lost the presenter names. So generating 3D molecular structures based on receptor binding sites with deep generative models. And I believe it's Matt Ragoza who will be speaking.
Yes, that's me.
Thank you.
Okay, sharing my screen. Okay, does that look okay?
It does, yes.
Okay. Hi, my name is Matt Ragoza. I'm a research staff member at the University of Pittsburgh, and today I'll be talking about generating 3D molecular structures from receptor binding sites with deep generative models. So a drug discovery requires us to search through an enormous chemical space to discover novel therapeutics. By one estimate, there are on the order of 10 to the 60th potentially drug-like compounds, and filtering this space down through each stage of the drug discovery pipeline is extremely time and cost intensive. At any stage of the pipeline, we could accidentally be throwing away life-saving medicines, so developing methods to rapidly explore and evaluate compounds is more urgent than ever. When the structure of the target protein is known, virtual screening is a method that enables us to screen compounds computationally. When you're given the structure of the target protein and the location of the binding site, as well as a database of potential binders, we can dock the ligand to the protein to generate poses and then score the ligand using its predicted binding pose. By repeating this process for each molecule in the data set, we can then rank and select the top scoring poses for empirical verification. The efficacy of virtual screening relies on the quality of the scoring function used to predict which binding poses are most favorable. In recent years, deep learning methods like convolutional neural networks have been used as scoring functions. These methods are able to exploit the large amounts of publicly accessible structural data that has become available, and they can automatically learn the protein-ligand interactions that are conducive to binding. When we train a deep learning model to predict binding affinity from a docked structure, in machine learning, this is known as a type of discriminative model. These are models that predict some target variable conditioned on input data. As in virtual screening, this allows us to estimate whether a given molecule will bind, but it's limited to screening known compounds, so it does not suggest new compounds to evaluate. This could lead to biasing our exploration of chemical space to compounds that are in existing databases. A model that's capable of generating molecules from a desired distribution, such as that of drug-like molecules, could overcome this limitation. But the question then becomes how to model such a complex distribution. Instead of mapping docked ligands to a score, we could train a model to map from a simpler distribution, like a standard normal distribution, to samples from our target distribution. This generative modeling framework would allow us to use deep learning to generate realistic molecules with desirable properties. Furthermore, we could train a model that alters this generative process based on some conditioning information, such as the structure of a target protein. Then the model can learn to generate favorable binding poses of active molecules directly from the receptor binding site. Currently, two kinds of representations are mainly used in generative models of molecules. These are smile strings and molecular graphs. Both are mainly 2D approaches, though there has been exciting work, as we have just seen, in the direction of 3D molecular graphs. Using these representations, generative models have been developed that condition on properties like solubility and drug likeness. However, generating molecules based on predicting binding with the receptor requires us to consider the 3D spatial interactions. So we represent atoms in a docked structure as three-dimensional Gaussian densities. Then we sum the density representations of each atom in the molecule on a three-dimensional grid with separate channels for each atom type. This is enabled by libmolgrid, which is a software package that was developed by our lab for GPU-accelerated molecular gridding. The resulting atomic density grid representation allows us to use a convolutional model architecture that can learn about the 3D spatial interactions between receptors and ligands. The architecture that we use is a conditional variational autoencoder combined with a generative adversarial network. From a high-level perspective, it learns to encode 3D receptor-ligand interactions, represented as atomic densities, into a learned latent space. Then it decodes ligand densities from that latent space when provided a receptor as a conditional input. The model is trained with a combination of three different loss functions. First, a KL divergence term constrains the latent space to follow a standard normal distribution. Second, the model minimizes the reconstruction error between the generated ligand density and the input ligand density. And third, a discriminative network is also trained to differentiate between real and generated ligand densities in the context of the binding site. Then the generative model is trained to fool the discriminator by producing realistic looking ligand densities. All three of these loss terms are combined to train the model. The goal of this type of architecture is to learn how to represent 3D receptor ligand binding patterns in a latent space, and then sampling this latent space to generate realistic ligand densities that have favorable interactions with the provided binding site. This allows several different ways of performing this sampling. The first is posterior sampling, where a real ligand is provided as the input, and the encoder outputs a mean and a standard deviation that are used for sampling the latent space. The generated samples will tend to be similar in shape and binding interactions as the input ligand, with some amount of variability. The amount of variability can actually be controlled by scaling the standard deviation that is used to sample the latent space. And we call this the variability factor. Because we constrain the latent space to follow a standard normal distribution during training, this allows us to perform prior sampling as well. This means that we do not provide any input ligand to the model, and we instead draw a latent sample from a standard normal distribution. Then we condition on a given receptor, and we generate a ligand which has no corresponding input at all. And instead, it's drawn from the predicted distribution of molecules that are predicted to bind to the given receptor. So we are able to generate ligand densities using this sampling procedure, but further processing is required to convert densities to 3D molecules. We accomplish this using a two-step procedure of atom fitting followed by bond adding. In atom fitting, we solve the inverse problem of converting a continuous density back into a discrete structure. This is solved as an optimization problem, where we find a set of atom types and coordinates that minimize a reconstruction loss between the generated density and the density corresponding to the fit atoms. Specifically, we can compute the density representation of a set of atoms using Libmol grid, and then this density representation is differentiable with respect to the atomic coordinates by design. So we perform an iterative process where we select grid points to add atoms to the current structure based on the grid density. Then we perform gradient descent on the atomic coordinates of the structure, and we repeat this process using the remaining grid density in a beam search. This atom fitting algorithm gives us a set of atom types and coordinates from a density, but after that, we have to do more processing to get a valid molecule. We add bonds to the atom types and coordinates using RDKit by taking into account the properties of the atom type and the geometry of the coordinates. We connect the disconnected atoms based on their distance and valence, and we use the atom types to determine things like the number of implicit hydrogens and aromaticity. The validity of the resulting molecules is assessed by checking for the number of disconnected fragments and RDKit sanitization errors. Finally, we perform Wiener energy minimization in the context of the binding site to relax the internal bond lengths and angles, and we use a pre-trained convolutional neural network to predict the binding affinity of the final molecule. We trained our model using the cross-docked 2020 dataset that was presented by Paul in this session yesterday. This is a dataset of docked compounds from the PDB-bind general set, where the native actives are all docked in each of the other targets as well. For more details on the data creation process, please see the paper for full details. We use the provided training and test folds. Specifically, we use the first train test split. We evaluated our models by selecting 10 PDB targets from the test set, and we considered using posterior sampling with 4 different variability factors, as well as prior sampling. For each target and sampling method, we generated 1,000 molecules. These plots show the fraction of the generated molecules that were valid and unique. As you can see, the model produces valid molecules at a high rate across all conditions. In addition, more than 90% of the generated molecules are chemically unique. As the variability factor is increased, the percentage of unique molecules approaches 100. indicating that whether an input ligand is used or not, the model is not just memorizing the same molecules. Certain targets appear to be consistently harder to generate valid and unique molecules, such as PDB-ID 5MKU, which only had about 62% valid molecules and 64% unique when using a variability factor of 1. In these plots, the distributions of molecular weight, the fingerprint similarity to the inputs, the Wien energy, and the predicted CNN affinity are shown for 5 of the 10 targets, which were selected at random. In each plot, the distributions for each of the different sampling methods are displayed in different colors, and the dotted gray line shows the value of the input ligand, which is a true active molecule for this target. It can be immediately seen that the prior molecules have wider variance in molecular weight and tend to be smaller. As the variability factor is increased, the molecules tend to get smaller and approach the distribution of the prior. The prior molecules are also more dissimilar to the input molecule as expected, since no input molecule was used to generate them. Increasing the variability factor tends to make the posterior molecules less similar to the input. The prior molecules and higher variability factor molecules had higher Wien energy and lower predicted affinity, which makes some sense because the input molecule is a known binder, so any variation chosen at random is not necessarily going to improve the affinity. However, it's interesting to point out that for each target, some molecules were generated that had a lower energy and a higher predicted affinity than the input molecule, which demonstrates that by repeated sampling, the model can potentially generate molecules with a higher binding affinity. These images show examples generated using the different sampling methods for a single target, which was PDB-ID 4PS7. The real active molecule, which was used as the input for posterior sampling, is displayed in cyan. The generated molecules are displayed in green, and they were selected based on their predicted affinity score. As you can see here, with a low variability factor, the generated molecules tend to have a more similar structure to the input, and they get more dissimilar as the variability factor is increased. The prior molecule is very different in structure and binding mode from the true active. So in this work, we have demonstrated the feasibility of generating 3D molecular structures from a generative model based on receptor binding sites. We introduced a novel algorithm for successfully converting continuous densities into valid discrete molecules. And in some cases, we were able to generate novel ligands with a higher predicted binding affinity than known active molecules. This work can serve as a starting point for performing continuous optimization of 3D molecular structures using the latent space that was learned by our model. That being said, there are many avenues for future work. We would like to train a model that explicitly conditions on the binding affinity as well as on the receptor binding site. In addition, we would like to integrate atom fitting directly into the training procedure so that we could impose energetic constraints on the generated molecules. Hopefully, these modifications would allow us to more consistently generate molecules with low energy and high predicted affinity. So with that, I would like to conclude my talk. A preprint of this work can be found on arXiv at the link shown here, and the code is all open source in this Git repository. So I would like to thank Dr. Coase and everyone in my lab for their guidance, their contributions and feedback. And of course, thank you all for your attention. And if there's any time, I would be happy to answer any questions.
Thank you, Matt. Are there any questions? And again, you